question is all about naming pieces of equipment. So if we look at them, we should be able to work it out. One is not, if it was a, so if we looked at what a picture for a measuring cylinder is, it would look like that. This is just basically a rectangle. I know it does have a bit of measurement things in there, but that is a beaker. This here looks like a funnel or even a filter funnel. If it had a piece of filter paper in it, would have something which looks like that. And the last item, which we've got there, looks like a cone. So this is, and it's a flask, so it's a conical flask. Next question is about indicators. If we imagine that we need to know about phenolphthalein, methyl orange, and UI. So we did firstly a little table, and if you got anything wrong, you could write this: acid, and then alkali, and you could do a little bit above, color in, and the first one would be litmus. Litmus is red in acid and blue in alkali. If we did, say, let's just change a pen. I don't think I really want a pencil actually. Then we did phenolphthalein, and you'll never be expected to spell it. You'll just have to learn it. It's colorless in acid and pink in alkaline solutions. The other one we have is methyl orange, which is red in acidic solutions and yellow in alkaline solutions. Now, the other thing I suppose that we could mention about this is obviously if we think we've got two which have got colour red in acid, and then obviously we've got UI. Universal integrated has got a variety of different colours in acids, but strongly acidic solutions, red. Then we've got some oranges, then yellow, green for a neutral solution, and then sort of blue and purple for alkaline solutions. So again, we can sort of see the colour blue is often associated with alkaline solutions, and purple is strongly alkaline. The next, so what colour is litmus is added to acid? What is the final colour? It's going to be red. So what I'd like you to do is put all the corrections on here, and maybe it might be worth putting any extra notes in. So when I check it, I'd like to make sure all corrections have been done, and also if there's anything else I would like you to write. Sodium potassium hydroxide, we know that's an alkaline solution. You may remember if we react potassium with water, we form potassium hydroxide and hydrogen gas. And the solution is alkaline. And why is that? Because it forms OH- ions in solution. So if it's an alkaline solution, it will be blue. Now this one is a sort of bit, does definitely require reading. So lead nitrate solution. So it's a solution. It means lead nitrate dissolved in water. So we know its state symbol is AQ. It's AQ. Potassium nitrate solution, AQ. And it says it forms a precipitate of lead chromate, lead 2 chromate. So a precipitate means it's a solid, and the other one is a solution. It says AQ. What's going to be the charge on the chromate ion? Here, we know from, if we look at our periodic table, hang on, where are my scroll bars? I find my scroll bars, I've lost, oh, there we go. If we look at our periodic table, you see potassium is in group 1. So if it's in group 1, it means it will have a charge of +1. So we've got 2 potassiums with charge of +1. So the chromate ion must have a charge which cancels out the 2 pluses because this has no overall charge, potassium chromate. So charge is going to be 2-. So that's how working out. Therefore, we can write 2- down. Next one is about an investigation. They place, and maybe one of the things that I didn't see on particularly anyone's work was it might be worth sometimes highlighting things. So 5 centimeters placed in a test tube, 1 centimeter cubed of lead nitrate is added. So this is basically linking to this, And it says allow the precipitate to settle and measure its height. That's another indication maybe there's a solid being formed. Repeat using separate samples of this and different volumes of lead nitrate. So we've got some results here. And what we need to obviously do is we need to obviously plot those and see what we get. So there's also going to be an anomalous result. So I'm going to just pause it there and I'll come back when I've actually drawn it. So we can see I plotted the points. Now it says plot the results. I would also ideally use crosses. It's just drawing on a computer is slightly different. So I would draw everything as tiny crosses. Then the next thing is the anomalous result. That looks like a straight line there. That looks like a straight line there. So that looks like the anomalous result there. Then ignoring the anomalous point, draw a straight line through the first 6 points. So 1, 2, 3, 4, 5, 6. Another straight line through the last 5 points. 1, 2, 3, 4, and obviously ignoring the anomalous one. So we're going to draw 2 straight lines. So insert shape, put a line in. Sure, 2 lines cross. Now it says find the volume that reacts exactly with 5 centimeters cubed of potassium chromate. So we kept on adding different amounts and the precipitate kept on increasing. So that means we still hadn't worked out how much had actually reacted to it. After we'd got to, obviously you can see here about 11 centimeters cubed of lead nitrate, the amount of precipitate remained the same. So it obviously all reacted because the height wasn't increasing and the lead nitrate was in solution. So the next thing we need to do is work it out. So what we'll do is we're trying to find a point where these 2 lines intersect. And it looks like, to me, that's 10. And then so if we work out the scale, 4, 4, 4, 4, so it's 0.4. So I would make that 9.8 centimeters cubed. The next bit is why did we get this anomalous result? So it's down here and we would have expected it to be up here. So maybe we had added too little lead-2 nitrate because that would be equivalent to us adding 6 centimeters cubed or 6 7 centimeters cubed of lead nitrate. Maybe we also didn't have enough of the potassium dichromate, which was yet another thing which was contributing to us having a precipitate. I suppose the other thing we could also have is maybe we didn't leave it for long enough because maybe it takes some time for a chemical reaction to occur and all mixing to occur so that we've got the precipitate to actually form. If you could please make sure you write down at least 2 of the reasons, that would be appreciated. The next one is about formation of a salt. So this is what we often expect, and sometimes they ask us to provide the method. So it says pour about 50 centimeters cubed of hydrochloric acid in a beaker, warm, and then we add small amounts of solid cobalt oxide and stir. So we're stirring to help ensure they actually react together. We're warming to help speed up the reaction because we heat things up to speed up reactions. And we have lots and lots of acid, and as we add cobalt oxide, there'll be less cobalt oxide until it stops reacting. We'll know this because most oxides are insoluble, so when it stops reacting, we should have excess cobalt oxide or solid forming at the bottom. We can then filter out the cobalt oxide, collect the liquid, and that's normally where we heat it until crystals form around the edge, then leave to cool, then filter and collect some crystals, but they've got an incorrect method here. So let's have a look at the questions and see what they say. So why is it not necessary to have a precise measurement of a volume of hydrochloric acid? So what we obviously want to think about is, I suppose, because we react all the acid, so all the acid is used up. So it doesn't really matter how much we've got, we're just trying to make sure all the acid is used up. Because all the acid reacts as we have excess cobalt to oxide. Why do we heat it up? It speeds up the rate of reaction, so to increase the rate of reaction. Why do we use glass? Glass is a poor conductor of heat, and also metals often react with acids. So glass does not react with acid. That's probably enough, but you could say but metals do. How will you say no, it stopped reacting? So this is the idea of the solid stops disappearing. I'll do some pictures to illustrate this in a second. So I just thought I would just draw some pictures to illustrate it. So we start off with our beaker. It's just got our HCl in. We obviously then, that was the world's worst drawing, I apologise. Heat it up. This obviously is going to speed up any reaction which occurs. We then add small amounts of CuO. If you think what's happening, the CuO will react with the HCl to form cobalt-2 chloride and water. That's a solid. Acids are aqueous. Cobalt rather. Oops, just changed that by mistake. Cobalt chloride is aqueous and water is a liquid. So we've got a solid and a liquid. And over time, we're adding lots of this solid here. And so that's using up, and eventually there will be no acid left. So we'll have a cobalt oxide and the cobalt chloride. We'll know we've added an excess of cobalt oxide because we will see at the bottom of here a small pile of the cobalt oxide. Then it says filter. So this is where we use our filter funnel. And we'll filter out our excess cobalt oxide, and into our evaporating basin we'll have our solution of cobalt chloride solution. It tells us in the question there is a small amount of a solid impurity that dissolves in water but does not react with the acid. So if we look at this, let's put some colour random specks in here. We've got two specks here of some impurity. And if we just leave it to evaporate off, which is what they've suggested as an incorrect method, this means we would have our crystals here of cobalt chloride, probably some water of crystallization in, and inside them there would also be that impurity here and here. However, if we do the correct method, which is basically heat the evaporating basin, obviously I'm not going to draw a tripod and things like that, eventually crystals will form around the edge here and here, and that's about, say, 100 degrees centigrade. We'll leave it to cool. Then we'll have our crystals, some sort of crystals here and here. We'll still probably have a little bit of solution left. We'll also have our impurities still floating in solution. I probably should have chosen a different colour pen because obviously impurities really should look the same each time. This has obviously been left to cool down, so maybe it's now 25 degrees centigrade. And now if we filter it out, in the filter paper, we have our crystals of cobalt chloride with a bit of water of crystallization. And what will go through is the solution and any impurities which are present. So that means we can now answer the last question, which is why will it not produce a pure sample? Is because the impurities will also be present with the cobalt-2 crystals, cobalt-2 fluoride crystals. So we now move on to the next bit. 3 different colours, write an equation. It says water is added slowly to this. The colour changes from blue to pink, so blue to purple and then to pink. Write down the chemical change from a purple solid. So let's see what formula purple solid formula is. So purple solid COCl2.2H2O. So the pink solid, it becomes a pink solid, so COCl2.6H2O. How do we go from here to here? We must react with 4 lots of water to go there. So that's our equation. Then it says what happens when the pink solid goes to become a blue solid. What we can see is we're going from here to here. What we're doing is we're losing water, so we can call that dehydration. It's losing water. So this is all about formula. Bromine. Now, one of the things you should remember, I know I might just show you on the periodic table. Let's scroll down. Certain elements exist as pairs. Now, if I can see if I can rotate this image, I'll pause that and sort that one out. Certain elements always go around in pairs. This is hydrogen. And if you imagine on the periodic table, you can draw a sort of what I would call, it looks something a bit like a 7, I suppose, or a weird sort of L. Now, these are the elements which always exist as pairs as elements. So that's as in H2, N2, O2, F2, CO2, Br2, I2, and AT2. And you may remember I told you the phrase, I have no bright or clever friends. That's one other way of remembering that. So, where did we get to? So, bromine exists as Br2. It reacts with water, H2O, and it forms HBr. Again, this is just using information in the question, and hypobromous acid plus HBrO. We can check its balance. We've got 2 bromines here, 1 there, 1 there, so it's balanced. Hydrogen, we've got 2 here, 1 here, 1 here. That's balanced. And then oxygen, 1 there and 1 there. So it's now a balanced equation. The next one says, show the empirical formula of this. It's a calculation question. So that means it's something to do with moles. So if we've got moles, you could think about trying to draw a magic triangle or write one equation down, which is, say, moles equals mass divided by mass of 1 mole. So we've got an equation here, and we could sort of think about what we know. Let's assume we've got 100 grams, so that means we've got 34.6 grams of copper, 30.52 grams of iron, and 34.88 grams of sulfur. So we know the masses. Mass of 1 mole, we can get those from a periodic table. Now let's pretend you maybe have forgotten which number you need. We've got iron here, so iron there, copper there, and sulfur here. It tells you the mass, if you look as a key, is the bigger number. So we're after 56 for that, 63.5 for that, and 32 for that. So we can find the bigger numbers are the relative atomic mass of 1 mole effectively. So we can do it as a little table. So you may remember doing this table, Fe, copper, and sulfur, 34.6, 30.52, and 34.88. 888. So that's mass. Then we could have AR, mass of 1 mole, 63.5, 56, and 32. So we've got mass of 1 mole. If we do that divided by that, we'll get the number of moles. So we could do this. So we can calculate the mass for each one. So that gives us 0.545. This gives me 0.545. I feel I'm winning here because I've got two of the same numbers, and 1.09. We can also put the word moles in here. We can also put a little ratio mark between that. Now, it looks sort of maybe like this is equal to that, and that's obviously twice that. So we could always also do the other idea of divide by smallest number of moles. So it gives me 1 to 1 to 2. So this is showing that for every copper, there is 1 iron and 2 sulfurs, which is what they asked us. Here's a question, a mole question. And what we obviously have to do is to work out how much calcium oxide could be formed when we've got 20 tons of that. So we could firstly think about what the equation means. It says for every 1 mole of calcium carbonate, we'd form 1 mole of calcium oxide. So again, we think about our equation. Moles is equal to mass divided by mass of 1 mole. Mass of 1 mole could be considered just the MR. So number of moles of calcium carbonate. So 20 tons. So that is 20 with 6 zeros on. 1, 2, 3, 4, 5, 6 grams divided by the mass of 1 mole of calcium carbonate. It tells us the mass of 1 mole of calcium carbonate, so that's helpful. So divide by 100 gives us, cross out those bits there. That means we've got 20. Sorry about the zeros, are not quite right, but that's 200,000 moles of CO3. So from the equation, if we have 1 mole of calcium carbonate, it would form 1 mole of calcium oxide. If we had 200,000 moles of calcium carbonate, we form 200,000 moles of calcium oxide. So now, this time round, what do we know? If we think about thinking about CaO, we could have our equation, moles equals mass over MR. We know the mass of 1 mole of calcium oxide. We know the number of moles, so we can say the mass is equal to moles times MR. Number of moles, 200,000 times the MR, which is 56, which gives us, so we do that calculation, we get 11,200,000 grams. We could write it as our final answer, or we could convert it back to tons by dividing by a million. So that's 1 with 6 zeros. So that's equal to 11.2 tons. So there we go. Last question. I think it's the last question. I'll just check. Last question. Wants to find the formula of an iron sulfate. So we've got some measurements. Firstly, they've got the measurement of an empty tube. The empty tube plus, say, okay, hang on 1 second. The empty tube, trying to find a colour brown to sort of represent iron sulfate, and we'll add some water in a second. And after heating it, all the water will have evaporated, so we'll have that. And then draw. So that's sort of trying to show the pictures. Oh, no, draw. Let's try a different one. Maybe I don't know why it's got an issue. Okay, so we've got the empty tube plus the iron sulfate and water, and at the end, the empty tube plus the iron sulfate. So why do we want to heat it to constant mass? Because we're trying to heat it up to remove all the water. So to remove all the water. The next bit said calculate the mass after heating to constant mass. So what we're trying to do is we're trying to compare the first value to the last value. So that's going to be 15.76 minus 11.96. So that's 3.8 grams of iron sulfate formed. Mass of water collected. If we look at the last two pictures, when it's got this one, it's got some water. After heating, it's lost the water. So the mass will be 17.56 minus 15.76. So that is 17.56 minus 15.76, giving me 1.8 grams. Find the value of X. This here again, if we think about moles, we could have our two headings. We know in terms of iron sulfate, we've got 3.8 grams. We know for the water, we've got 1.8 grams. We know the mass of 1 mole of iron sulfate is 152. So 3.8 over 152 gives me 0.025. And again, that's moles. Water, 1.8 over tells us mass of 1 mole of water. Gives me 0.1. That's a ratio. To make it simpler, we can divide both by the smallest number. So that divided by 0.025 gives me 1. 0.1 over 0.025, as in 0.025 gives me 4. So for every iron sulfate, there are 4 waters, so X equals 4. So once you put all the corrections on your paper, what I'd like you also to do is make sure you highlight anything you'd like me to go through again in class, or at a different time with you in, say, a surgery, or some break time or lunch time, or anything you'd like sort of further clarification on. And also maybe if there's anything, steps which you'd like me to just go through again with you in person. So I hope that was helpful. Thank you.